continuing on with physics in 24 problems, 24 questions. I can't remember what I said. But the goal here is to pick 24 problems from this textbook, Halliday, Resnick and Walker, just because it's more popular. Solve those problems as a way to kind of like, hey, here's the important things you need to know in physics. So we are, and I'm not doing every single chapter. Didn't do chapter 1, boring. And there's a couple other ones I'm not going to do. And I'm going to skip over some stuff because I can't do everything. And this is no substitute for actually studying physics. This is for entertainment purposes because I'm entertained. Okay, so we are in chapter 5, force and motion. So let's just think about what we've done so far. The first thing we did was motion in a straight line, so scalar kinematics. And then we did vectors, and then we did motion. I'm skipping something. And then we did motion in 2D. Yeah, I guess that's it. So here we are, chapter 5. Yeah, because I did 2, 3, 4, and this is 5. Okay, so now we haven't talked about forces at all. So we have a lot of stuff to talk about forces. We're going to go over Newton's 3 laws. But first, let's start with Aristotle. And I know that seems silly, but I'm just going to write Aristotle so we can remember Aristotle. And I'm going to underline it. And it's important to realize that the Greek philosophers thought about forces. They didn't say forces because they spoke Greek, and they didn't really have the same terminology that we have now. But one of the ideas that Aristotle came up with was that if you leave something alone, it's going to go back to its natural state, which is at rest. So if you take a block and I push it, I push this block, then while I'm pushing it, it's going to move, and when I don't push it, it doesn't move. Very, very, very sensical, common sense idea. It's the way a lot of people think about the world. Aristotle didn't do any experiments on that. He just said, come on, it makes sense. Let's just do it that way. If you push something, it moves. If you don't push it, it doesn't move. And his ideas about motion were the way it was supposed to be, right? That's what everyone believed for a long time. Eventually, some people came along, Galileo, Newton, and others, and started to realize that that wasn't quite true. You could have an object moving and no forces acting on it. You know, if you take a ball and let it roll down an incline, it'll speed up. And that's one thing, right? Because Aristotle also said if you drop something that falls, heavier things fall faster. He never checked it. Not true. And so what they did was to roll it down this track so that you could do things in a much slower scale. And they realized if you got it almost level, you could get the ball to roll at a constant speed. And then they kind of said, well, maybe in an ideal world, it could be horizontal and constant speed. And that's how we get to Newton's 3 laws of motion. So I want to talk about Newton and his first law. So Aristotle said that if you leave something alone, it's going to stop. And Newton says, wrong. And people get mad when I say this. They say, oh, Aristotle's wrong. That's not Newton's first law. That's not what that says. No. But that's essentially what it said, right? He says that if you leave an object alone, it's going to move at a constant velocity. He didn't say it like that because that's English, right? But that's basically what he said. Aristotle says the natural state of motion is at rest. Newton says the natural state of motion is constant velocity. And that's the first law. Okay, so you can say, oh, if you an object will move at a constant speed and direction unless acted on by a force. That's what that says. It says that the natural state, if you don't do anything, it moves at a constant speed. Newton's second law says this. This says a lot of stuff right there, and you could even say that's the first law is redundant if you have that one, okay? Newton's first law says that if you apply a force to an object, it will have an acceleration. And the value of that acceleration is inversely proportional to the mass. If you increase the mass, the acceleration decreases. The value of the acceleration is proportional to the force. and that's the net force. And we have this as a vector equation, but it really wasn't. It really, I mean, vectors didn't come along till later. But that's the idea, right? And then you can say, okay, if F net vector is 0 vector, that's going to be mass times acceleration, 0 vector. If the acceleration is the 0 vector, constant speed, constant direction. Newton's first law. So Newton's first law doesn't make sense if you have Newton's second law. Newton's first law makes sense if Newton says Aristotle's wrong. I already said that, but I just want to emphasize that because people get a little upset. Okay? So, but that's Newton's second law. It's a relationship between, it says, what do forces do to an object? They change the motion. Change is in the acceleration, and it actually looks a little bit better if you write it like this. I'm going to write it as F net is mass times dv dt, right? That's the acceleration. And there are other ways to write this. We can write this in terms of momentum, but I'm going to follow along with the book, and it doesn't do that yet. So that's Newton's second law. Forces change momentum, change velocity, change motion. Okay, now we have the third law, and it looks like this. Let me just draw a little picture. A, B. So imagine these two objects interact with each other in some way. Then I can say that the force that there's some force that A pushes on B, and then there's some force that B pushes on A. Forces are an interaction between two objects. That's what Newton's third law says. And those forces are equal and opposite. So if A pushes on B, B pushes on A with an equal and opposite force. That's what Newton's third law says. Okay. It's the same as saying this. Let's see if I can draw it. That's the United States. Okay. And then here's LA and here's NY, New York, Los Angeles. And this says if I go this way, and it's what, 3,000 miles, then to go from New York to LA is 3,000 miles the other way. It's really the distance between them. You can't have a distance in one location. It's a distance between two things. It's a force between two things. And there's a lot more stuff there. I do want to point out one more thing. Let's go back to, that's going to come up some. One more thing about Newton's second law. Let's write it out. F net mass times acceleration. And this is the net force. Does this use net force? Sometimes you'll see it looking like this. The sum of the forces equals mass times acceleration. But I don't like writing the sigma symbol all the time, so I don't do that. I write F net. But it is the net force. So suppose I have a simple situation of a block on a plane like that. Then I can have forces, the gravitational force, mg, the normal force, n, and some frictional force, F friction. And those are my net forces. And I can draw them as a free body diagram. That's what this is, a free body diagram, where I draw a point and I draw all the forces acting on it. Now, later, we're going to draw diagrams a little bit later where we don't just describe the object as a point. But for now, it's a point, and that's a free body diagram. And then you can pick your x and y axis. It doesn't really matter. They're not real, so you can pick them wherever you want. Now, the important thing, though, is that for this object, suppose I draw a simpler free body diagram. Well, simpler and more complicated. I didn't start off with my problem. You know, I said I'm going to solve problems, so that's my problem, but I'll get to that in just a second. Suppose I have a block B and a block A. Let's draw two free body diagrams for both blocks, and suppose they're at rest. So on A, I have the gravitational force MAG, and then I have a force that I'll call this FB pushing on A. And then for block B, I'm going to draw it right here. I have the gravitational force MBG, and then I have the table, I'll just call that N pushing up. But what about A? Do I use the mass of the two together? No. So what if B pushes on A, then A has to push down with the same force, FA on B, right? So but be careful when you're drawing your free body diagrams that you only draw forces on that object. I don't want to put this force on that, right? Because then that's not the way it works. These all have to be forces on object A. These are forces on object B. Okay, one final thing, and we will get to our problem. So we have a couple of special forces here. So we have the weight, and we'll look at this in way more detail later. But near the surface of the Earth, if you're standing on the Earth, there is a gravitational force that we call the weight. You could call it Fg, you could call it W, and it's equal to mg, where g is that gravitational field 0, negative 9.80 newtons per kilogram. And that is the gravitational field. It's also the acceleration of a freely falling object, but I like this better. And it will make more sense when you get to electric fields. It's the gravitational field. But near the surface of the Earth, that gravitational field is constant and down. And that's a special force. Now, the book talks about some other special forces that are much more complicated. Well, I've already mentioned this one. I have mg, the weight of a block, and I have what we call the normal force. The normal force is an interaction between an object and a surface. There's no equation for it. It's what we call a force of constraint. So that means that it is whatever force it needs to be to do whatever it needs to do. Okay. Why is that dark over there? Imagine that I push down on this with my finger, and I increase another force pushing down. Well, in order for the block to stay at rest, the normal force is going to have to increase. So it just does whatever it needs to do to make the block not go through the table or the surface. And it's not always up, right? I can have a block like this, and I can push that way. In that case, I have a gravitational force, I have a frictional force, I have my force, and the normal force pushes perpendicular to the surface. It's normal. Another force that's very similar is the tension. So if I have a rope going over a pulley like that, the tension in the rope does the same thing. It provides a force to prevent that thing from stretching. The difference is that it's in the direction of the rope. And if we have massless ropes and strings, then every point along there, the magnitude of the tension is the same. Finally, we have the frictional force. They just say it's parallel to the surface, but I think in this chapter, all the situations deal with frictionless cases. Okay, I think I got all of that. All of that. Let's see. Is there anything else important in there? Force, Newton's weight, normal force, friction, Newton's third law. Okay, good. Let's do the problem. And I didn't work this one out beforehand. I saw it had 3 dots next to it, so maybe it's difficult. I don't know what the 3 dots mean. I didn't read the intro. I'm not that kind of person. Okay, so here's the problem. We have these 3 blocks connected by strings. Oh, and you can't quite see, but that's block A. I cut that off a little bit. And you can't see the messes. Okay, so block A is 6 kilograms, 8 kilograms, 10 kilograms. Hold it there, let it go, and find the tension in this string right there. That's the goal. It might be fun. The only thing that this does not have is vectors at angles, but that's fine. It's still going to be a great exercise for us. So what I want to do is to draw 3 free body diagrams. One for A, one for B, one for C. Let's just do it. So here is my free body diagram for A. So when you're drawing a free body diagram, you want to think, what's touching that and what long-range forces are acting on that? In this case, there's only one thing touching, and there's only one long-range force. There's the gravitational force and the tension. So I'm going to write this as pulling down MA, G, and then this is T. Now, do I know the value? Can I just think about the values of those? And the answer is no, I can't, because I can't say anything about those because I don't know the acceleration. If this is at rest, then yes, the tension would be equal to the weight. But it's not at rest, right? If this is 10 kilograms and that's 6, this whole thing's going to accelerate that way. So this is going to accelerate up. So let's just say it's going to accelerate up. Now let's do block B. Here's block B. It also has a gravitational force, mbg. It has a normal force, N. Now it has two strings pulling on it. It has this, I'm going to call this T1 and T2. And so T1 pulls up on this one, so it's going to pull to the left on that one. That's the same string, so it has the same tension. Now, I drew those as the same, but they're not the same, right? These are not going to be the same tension. Let's draw that one a little bit longer. I already said, that's T1, T2. I already said it's going to accelerate that way, so it has to have a greater force in that direction. And then finally, I'm going to have block C. It's going to look like this. It's accelerating down, so I know its gravitational force mcg and the tension T2. Okay, now we can just start. The goal in a lot of these problems is to write down a bunch of equations that you can solve, or a mathematician can solve. So let's just use Newton's second law right here. I'm going to call this my x and my y axis. So Newton's second law for this says that F net equals mass times acceleration. But there's no forces in the x direction, so I don't really care about that. Let's just write this as F net in the y direction. And that's going to be equal to T1 minus MAG equals MAA. So there's a lot going on here, right? So first of all, I have the tension going upwards. And I here put a negative because it's not a vector. It's the y component. The y component's in the negative direction, so I put it in MAG like that. And then I have mass times acceleration, and the acceleration is in the positive y direction. So this is an equation that I'm going to use. Now let's go up here to this one. I'm going to write down the net force in the x and the net force in the y. Let's start with the y. F net y, I have N minus MBG equals 0. Because the block stays on the surface, it does not accelerate up or down, so it has to have a vertical acceleration of 0. And this tells me that the normal force would have to be equal to the weight, but I don't really care. Okay, so it doesn't really matter. But I did it. And then we can do F net in the x direction. That's more important. So here I have T2 minus T1, and this is accelerating that way. It's going to be equal to MBA. That's the positive x direction. So there's another equation. Finally, I can write down the equation for that one. This one's going to accelerate down. I have F net y is T2 minus MCG equals negative MCA, right? Because it's accelerating down. That's another equation. So you'll notice that I have 3 equations, and I have 3 things I don't know. I don't know A, I don't know T1, I don't know T2. But other than that, those equations have those 3 variables in them. So we're going to solve 3 equations, 3 unknowns. It's not so bad, right? I'm erasing that. Hope you don't mind. Okay, so I don't really care about the acceleration. I care about T2. That's what the problem asked for. So let's just solve this one for the acceleration. So A is going to be equal to T1 over MA minus G. I just solved that for A. Now I'm going to plug in that over here for A. So I get T2 minus T1 equals MB T1 over MA. Let's see, wait. And then minus, I'm plugging in that, minus MBG. Let's go ahead and solve this for T2. So T2, I'm going to add T1 to both sides. I get T1 times 1 plus MB over MA minus MBG. Now I can plug that in over here to this equation for T2, and, oh wait, I guess I should solve this for T2. That's a little weird. I should have solved this for T2. I should do that one next. I haven't thought this out. You know that, right? Okay, so I don't. This is. That's a good one right there. Let's put that in over there and solve for T2. So I get T2 equals mcg minus mca, which is going to be T1 mc over ma, and then I'm multiplying that by mca, so minus mcg. Okay. Now, so I used this equation and I used that equation. So right here, I'm going to solve this for T2. So T2 is T1 plus MBA, OA. And then I should put in, maybe I did this not in the best way. Well, just keep plowing on, right? I didn't think of this beforehand. So, and then so if I put in A, I get T2 equals T1 plus MB times A, which is that, T1 over MA minus MB G. Okay, so now I have T2. I can plug in that right here, and I should be good to go. Okay, so I'm going to erase some stuff, hopefully not critically. So this T2 and that T2 are equal, so I get mcg minus T1 mc over ma minus mc, I feel like I made a mistake, equals T1, bad decisions. This is what happens when you don't work out the problem beforehand. T1 plus MB T1 over MA minus MBG. And it's a shame because I thought my intro was really well. I hate to do this, so I'm going to plow through. Okay, plow through. So I'm going to add T1, this term to the other side, and that term to this side. I get MCG minus M. Oh, those cancel. Is that right? Huh. Okay, so now I'm going to bring these to the, bring that over there, bring that over here. MBG equals T1 times 1 plus MB over MA plus MC over MA. And then so T1 is equal to MBG over 1 plus MB over MA plus MC over MA. Don't worry, I'm going to get this another way. And now I can go back up here and solve for T2, which I deleted. T2 minus MCG equals negative MCA. Ugh. Okay, I got it, right? I'm not going to finish because it's just algebra. I'm going to show you another way to do this because there's a little trick. I can get the whole thing. Let's think of this as one system. The whole system has to accelerate. So it has a mass of MA plus MB plus, that's A, plus MC. Now, what's the net force acting on my system in just a non-dimensional terms, right? Non-directional terms. Well, I have a gravitational force pulling in the direction of motion. That's going to be mcg. And then I have a gravitational force pulling in the opposite direction of motion, and that's minus mag. So the net force is going to be the difference of those two masses. So it's going to be g times mc minus ma. And that's going to be equal to the mass total mass, which I'll write it as ma plus mb plus mc times a. So now I can find a very easily. A is just going to be equal to mc minus ma over ma plus mb plus mc times g. And you'll notice this has no units right there because they cancel, so I get meters per second squared, meters per second squared. Now, if I know the acceleration, I can go back up here and just look at this mass right there. I know the acceleration, so I can find the tension. So T2 minus mcg equals ma, right, but minus. But I know that, so it's going to be equal to, I can just solve it for one fell swoop. T2 is going to be mcg minus that, so minus the total mass, which is this. No, that is C. Minus mc times g times mc minus ma over ma plus mb plus mc. And that's that. I should work out the problems before I do them, just to make sure I know what I'm doing. Because it had the 3 dots. I was like, oh, it'll be fun. And it wasn't fun. The 3 dots were because it was 3 equations, 3 unknowns. So it was a math problem, not a physics problem. But setting up those 3 equations, from the 3 Newton's second law, that's the physics part. The rest is math. So there still may be an error in there, but I don't care. We're still learning physics. Playlist down below. Hope you enjoyed that.